Hi everyone, my name is Lindsey Jacobson. I am a student in aerospace engineering, and for the past 2 summers I've been an engineering intern with the James Webb Space Telescope program. And today I just wanted to provide you an overview of Webb's deployments. All right, so let's get started. So as some of you, or hopefully most of you know by now, Webb is an observatory that's going to fold up to fit in the rocket it's going to launch in, and then it's going to unfold and deploy when it's out in space. This sort of arrow on the right of the screen shows the major deployments that are going to happen in this process, and we're going to get into the details of those today. But what's really unique about this is that there's 178 things that could go wrong with all these deployments. Specifically, there's 178 deployments and releases that must be completed successfully for Webb to be fully operational in the way that it's supposed to be. So there's been a lot of detail in the design to make sure all of these deployments occur as they're supposed to and as smoothly as possible. And there's a lot of detail beyond what you might even think of. When I was working with Webb, one thing I learned is that contamination control is even important to complete these deployments, because if there's some contamination, substance, or material where it's not supposed to be, some of the deployments might not be able to occur as they're intended to, as the mechanisms might get caught. So a lot of detail has been put into this process, and there's been a lot of analysis and verification to make sure everything's going to go smoothly as possible. And these deployments are also critical to Webb's ability to achieve its science goals. Each of these deployments has a specific purpose. The solar array, for instance, provides power. The tower is used for thermal isolation. The aft flap is used for momentum management. The Sunshield is used for thermal control, which we'll get into later. And the cord fold wings are used for imaging. So those are the final stages of unfolding the mirror that allows Webb to collect enough light in the right orientation to get its beautiful images. So we're going to get into that in just a second. But first, I just wanted to provide you with an overview of Webb's major components. It'll kind of give you an idea of what I'm talking about throughout this presentation. First, there's the primary mirror. That's the big shiny gold hexagon that many of us know Webb by at this point. Then there's the spacecraft bus on the underneath of Webb. That's kind of like the brains of the observatory. It holds all of its data processing, communication modules, all that sort of good stuff. Then there's the secondary mirror, supported by the SMSS, also known as the secondary mirror support structure. The Sunshield, that is an incredible mechanism, or at least it can be honestly considered a subsystem in itself that we'll get into later. The aft radiator, which helps dispose heat out the back from all of the different instruments. The aft flap, which helps control momentum management. And also the solar array on the underneath, which is responsible for collecting sunlight to convert into electrical power. So I'm just going to run through all of these deployments sort of in the timeline that they're going to happen. All right, so I just wanted to give you an overview of all of the deployments as they're going to happen in the sort of rough timeline that they're scheduled to happen on the mission. So first are the post-launch procedures, and those are pretty standard for any kind of mission that's going to be launched. First, Webb will be launched on an Ariane 5 rocket from French Guiana. Then motors are going to be jettisoned at maximum acceleration. The payload fairing will be later jettisoned. The first stage will separate, and then the upper stage will carry Webb a little bit further. During this period of time, slow rotations are going to be made where Webb just kind of rotates back and forth to protect the observatory from heat and radiation. Webb was designed to be operational in cryogenic temperatures, and any excess heat or radiation that it's exposed to, especially for prolonged periods of time, does have the potential to do some damage. So we want to avoid heat and radiation buildup as much as possible. After this happens for a little bit with the rolling back and forth, the rolling stops, and the observatory officially separates from the upper stage and continues its journey to its final destination. Now that the observatory has fully separated from the rocket, it is responsible for getting where it needs to go, and as such, it needs to generate its own power. So the solar array deploys to collect sunlight to convert it into electrical power. And that way, this array satisfies Webb's power needs for the rest of the mission. During this time, the onboard control systems sort of comes on and begins to monitor attitude. The attitude or sort of orientation of the observatory is controlled to maintain power generation, just to make sure that the solar array is always in an orientation where it can collect sunlight, and to provide thermal safety for the same reasons I mentioned earlier. Webb is going to be kept at cryogenic temperatures eventually, and we don't want it to get too hot at any point in the mission. So these attitude adjustments are going to help maintain those lower temperatures. So next is mid-course corrections. So velocity additions have to be made pretty early in the mission in order to get Webb on the right trajectory and to preserve fuel. So making these velocity additions early means we don't have to make as many adjustments throughout the course of the mission, which is really important because it allows us to preserve fuel, which can hopefully extend the lifetime of the mission. In addition, the trajectory has been designed to avoid using a retrofire so that Webb doesn't have to point at the sun. This is really helpful again because it prevents extra exposure to sunlight and heat. Finally, thrusters are only located on the sunlit side of the observatory to preserve mirror cleanliness. This is really important from a contamination control perspective. As you guys might know, if you have a camera or something of the like and you have dust or something smudged on the lens, you're not going to get a good picture. And the same is true for Webb. Any of the kind of materials or substances that might come out of the thrusters could have the potential to create contamination on Webb's critical surfaces, the mirrors or the instruments. And this contamination could be really problematic in terms of imaging. So a lot of design considerations were made to prevent contamination on orbit, and this is just one of them. And then next we have tower separation. This is the next major deployment section, but first the Sunshield pallets must deploy. Those are kind of the silver kind of structure coming out the screen in that picture towards you. Those are really folded up in the observatory like this, and those just fold down forward. And so those are what's going to hold the Sunshield in place. Following this, the tower separates from the telescope, and this separation is really important for providing thermal isolation. This deployment takes quite some time, but it helps start to let the observatory start cooling down to its operating temperatures. Thermal isolation is really important for another thing that you might be familiar with. There's another analog. If any of you guys have ever used an infrared camera, you know that it detects heat signatures, and you can look at what areas of a image are sort of like hotter. The same is true for Webb. A lot of Webb's observations are going to be made in the infrared, so we need to block out those heat signatures as much as we can so that we can get clear images of what we really want to see, which are those galaxies and just other aspects of the universe that are so far away. So we really need Webb to be as cold as possible, which is why it's going to operate at cryogenic temperatures. The first thing that helps us achieve this is the tower separation. Finally, on this slide, the aft flap deploys, which helps manage momentum and then in turn manages fuel consumption, as we've discussed previously. The next deployment is one of the most exciting ones on here. Hopefully you've been excited for it. It's one of my favorites to talk about. It's the Sunshield deployment. So the Sunshield is a really amazing structure. It's roughly the size of a tennis court, and there's 5 layers of it, each of which are extremely thin. And what's really interesting about the Sunshield that I've sort of learned from talking to engineers on the project is that it's really hard to deploy what they describe to me as floppity mechanisms. That is, mechanisms that can sort of deform. They're not rigid. They do this little kind of wobble thing because they're sheets pretty much, essentially. And it's really hard to be able to deploy these with great accuracy and safely. So a lot of time and effort has gone into the design of these structures, well, these Sunshield layers, to make sure that they're going to deploy properly and safely to keep everything cool. First, the first thing that has to deploy correctly for the Sunshield to complete its deployment is the membrane restraint devices. These are also called MRDs. There are so many of these scattered around the Sunshield, and they each kind of help the Sunshield unfurl in its little own self-confined section. These MRDs, since there's so many of them, their design was really detailed, and analysis and verification of these devices was very detailed as well. They went through critical reviews and failure modes analysis to make sure that they're going to be as reliable as possible and to provide the highest confidence in them. Next, the protective covers roll back, and then the mid-booms extend. Those are some sort of horizontal structures that go under the Sunshield in the center that help it assume its hexagonal shape. Finally, the Sunshield membranes are tensioned and the instruments begin to cool down. The tensioning has to be really precise because this is a really detailed thermal system. There's a difference of 600 degrees between the cool side and the warm side of the telescope. And this is just really incredible. The venting between each of the layers is responsible for that. And so all of these deployments are just so incredibly precise. The Sunshield's a really amazing subsystem, and it's really incredible to see the engineering work that's gone into it. Moving forward, we have the secondary mirror deployments. The secondary mirror support structure is kind of folded up at first, and then it folds down forward, carrying the secondary support, the secondary mirror. And what's really interesting about this deployment is it's really hard to test something like this in Earth's gravity. This deployment was designed to take place in zero gravity and space. And so we have to be really creative when we're replicating these environments on Earth, because we like to test like we fly, just to provide confidence that it's going to work in the conditions we fly in. So one thing that they do, I don't know if you can see it in this picture here, but on the bottom you can sort of see some cables that sort of support the SMSS during these deployment tests. And these cables are intended to help offset gravity, or at least simulate what sort of zero gravity would be like. We also use ground support equipment, and we do some verification by analysis and simulations to really creatively figure out ways we can verify these deployments and have high confidence in them. And then finally, after this, the aft deployable radiator releases so that instruments can dispose excess heat into space, which is important for reasons discussed earlier. We've got to be really, really cold, really cryogenic. Next, the primary mirror deployments take place. This is kind of what makes Webb the special shiny hexagon that we know it is. So the process is sort of shown on this slide. One wing unfolds, and then the next wing unfolds, and that makes Webb the hexagon we know it to be. These deployments take quite a bit of time, but they finish out the major deployments on the observatory, which is really exciting. Following this, Webb continues its journey to L2. During this time, it continues to cool down to operational temperatures, and it gets ready to start its commissioning process once it gets there. L2 is really unique because it's a location where Webb can orbit in lockstep with Earth. So basically, as Earth moves around the sun, the Webb observatory is going to rotate around with it, which is really important because it's going to help Webb block out sunlight and heat, both from the Earth and the sun as it travels throughout its journey. That means that anytime in its mission, it's going to have this really stable thermal environment, which is really important for its imaging in the infrared. And so Webb will undergo a trajectory correction on the 29th day, roughly, after launch, which is going to put it into halo orbit there. And it's going to be pretty far away when this happens. That's something that a lot of people may not recognize about Webb at first. Whereas Hubble orbited in low Earth orbit, as you can see it close to the Earth on that image in the bottom there, Webb's going to be really far out. The moon, for example, is about 400,000 kilometers out. Webb's almost 4 times as far out. This makes it really hard to service it. We really might not have an option to service it, probably not. Hubble, on the other hand, we could go fly shuttle missions to fix it, maintain it, perform other necessary maintenance procedures, but we really can't do the same thing for Webb. And that's why it's so extremely critical that we get all of this right the first time, and why so much detail has been put into this design process, the integration, testing, and verification of Webb, just to make sure that everything is going to go perfectly smoothly once it launches. Once Webb gets to L2, we have the final period of commissioning. Commissioning is going to take quite some time, around 130 days, but it's really necessary to make sure that all of the instruments are performing as needed. So first, the scientific instruments are going to power up, and then the observatory is going to demonstrate that it can lock onto targets and collect data with NIRCam, the near-infrared camera. Next, the telescope optics are going to be aligned using wavefront sensing and control techniques. which is a really incredible process. I'll try to describe it here. So basically, the observatory locks onto a target, and then each of the 18 mirrors takes an image of what that target would look like from its perspective. All of these images are combined, and they sort of try to figure out where all of the mirrors should be so that all of those images are in focus. Then the mirrors each individually update their position so that they're all in alignment. And this alignment happens down to picometer precision. That's 1/10,000th of a human hair in width. That's how precise these adjustments are. So this whole process is incredible. It's incredible that they were able to figure this out and put this together, and you can read more about it on the JWST website. It's one of my favorite parts of Webb. It's so fascinating. And then next, finally, the instruments are calibrated and the ability to track moving targets is demonstrated. This helps Webb see things kind of in our backyard in the solar system, like asteroids, planets, other things that are closer in proximity to us. And then finally, early release observations are going to reveal the capabilities of the observatory. This is going to be really exciting. It's going to be when Webb gets to show off all of the fantastic images it takes to the scientific community and to the rest of the world as a preliminary sort of understanding of what the observatory is capable of. So I'm so excited seeing those images. I'm so looking forward to it, and just kind of keeping up with all these deployments as they happen in real time. So thank you so much for listening to me today. It's been a pleasure to speak with you, and I hope you're as excited as I am to see all this come together. Thank you so much.